back. We're doing the session on YouTube, so I just want to make sure that our volume and video and sound, everything is fine. So if the volume is not fine, then please do send us a comment. And internally also, if volume is not fine, please send a comment. I hope everything is fine. So if something is not clear, if the volume is not clear or the video is not clear, if something is not working properly, please do send us a comment. I'm going to keep talking for about 5-10 seconds before we go to the question. I want to make sure that the audio video technology issues are all completely fixed. And the class itself is a lot of fun. And we're going to do a bunch of questions, 8 to 10 questions, non-routine, different, wacky, interesting, all good. But I want to make sure that the audio video part works fine. I'm just going to have a look at the comments to see whether the chat window is fine. I'm going to type something to know whether the chat window works. I'm not getting any comment. I'm just waiting for some feedback saying that the chat window is working fine and the videos are working fine. The video is working fine. The video is clear. The video is working fine. For some reason, I'm not able to connect to the chat. For me, I get a message saying I'm not able to connect to the chat. That's all right. It'll get fixed automatically, I think. But I hope the video and audio are clear. I'm just going to spend some couple of seconds to see. Something seems to be wrong with my chatting screen. That's all right. So I won't have access to the chat, but I'm going to jump in and do the questions anyway. Lovely. I hope you've seen quite a few of these questions. We're going to try this one. Fine. I'm going to give you a minute to read the question and then we'll jump in and solve this. 3 people each thinking of a number which is a product of 2 different primes. The product of the 3 numbers which are thought of could be 3 different people thinking of one number. Each of those numbers is a product of 2 primes. Then we multiply the 3 numbers. What could the product could be? And it sounds like a really big question. And so some of these questions where it seems like you are used to living in a world where it says find this number, calculate the average, find the largest possible, write this differently. So all those are routine questions. I don't even understand this question. And then answers also, the question also, which of these could be? That means only one of these could be. The other 3 will not be. Something is wrong with them, that it doesn't fit into this criteria. What are the criteria? 3 people there. And each of them thinks of one number. Each of those numbers is a product of 2 primes. So I'm going to say, let's say the first person thinks of 2 numbers, P1, P2. Why am I writing P1, P2? They're prime numbers, P prime, P1, P2. Second person thinking of P3, P4. When I write P3, P4, I mean P3 into P4, P1 into P2. This is one number, this is one number, this is the third number. And so first person thinks of P1 into P2, second person thinks of P3 into P4, third person thinks of P5 into P6, where P1, P2, P3, P4, P5, P6 are all primes. Product of 2 primes is a number, product of 2 primes is a number, product of 2 primes is a number. P1 into P2 into P3 into P4 into P5 into P6 could be one of these. That means it cannot be the other 3. Only one of these is a possible answer. He's not saying it should be. Quite likely there are many. I could have P1, P2 as 2, 3, 11 and 13, 17 and 19. That will work. Right? So there are many possible answers for what it could be. But only one of these 4 is a possible answer. Other 3 are not possible. We'll obviously have to go step by step and look at these numbers. I'm going to rephrase this question. Could the product be 120? I have a scenario where with P1, P2 sitting here, P3, P4 sitting there, P5, P6 sitting there, I multiply all of this, P1 into P2 into P3 into P4 into P5 into P6, and that product is equal to 120. So like several questions that you're likely to see in number system, number theory, it starts with prime factorization. Fine. So you should learn this art of looking at numbers in terms of their prime factorization. And so I'm going to start off by looking at 120. What do? I take 120. You can write it like this and divide and go. I'm not going to do that. 120 is 12 into 10. 10 is 2 into 5. 12 is 4 into 3 or 2 square into 3 into trying to do non-routine questions. So you need to figure out mechanisms where the mathematical understanding is intuitive, it's natural, it's clear in your mind, and also the mechanical part you're able to do quickly. You cannot say 12 is 2 into 6, then 2 into 2 into 3. You say 12 is 4 into 3, 2 2s into 3, 2 square into 3. 10 is 2 into 5. So finally what do we have? 2 cube into 3 into 5. I have to put this into 3 boxes. It's like I have 3 2s with me, a 3 and a 5. I can put a 2 here, a 3 here and a 5 here. I have 2 more 2s. I'll put 1 here, 1 here. I'm not saying this is how it will be, but I can distribute like this, the 3 numbers. But hey, we have a problem. We are told each of the 3 numbers is a product of 2 different primes. In this case, we don't have room for a second different prime here. 3 and 5 are here, then 2 is here. Maybe I can put another 2 here, but I don't have a room for another different prime here, or 120 cannot be the answer. I cannot have 120 as a product of these 3 numbers which satisfy this condition. The product of 2 different primes. Or you should think about it right now, right about this time, you should be saying, okay, what kind of product will work? Started with trial and error. You started by saying, okay, I'm going to try 120, see if 120 works. But the moment you go ahead trying 120, you should immediately be saying, okay, 120 didn't work. Why didn't it work? Or what might work? Can I find a method for what could work? Then you can skip off several steps and jump to the answer. What will work? I need to have 6 primes straight away. I want P1, P2, P3, P4, P5, P6. Straight away this is saying my 6 primes need not be distinct. If this number had been 2 cube into 3 into 5 into 7, that would have worked. So I can have 2 cube into 3 into 5 into 7. 2 and 3, 2 and 5, 2 and 7. That works. So my P1, P2, P3, P4, P5, P6 need not be distinct. I could have P1 repeating. I can have a 2 cube. But I'm in the end having 2 primes here, 2 primes here, 2 primes here. So when I prime factorize, and I think of it as 2 cube into 3 into 5, if I think of it as 3 2s, a 3 and a 5. I'm not going to think of it as 3 primes. I'm going to think of it as 5 prime factors. 2, 2, 2, 3, 5. Like that, I need to have 6 because I'm going to put 2 in a box, 2 in a box, 2 in a box. Does not add up to 6 and put 2, 2. It's a beautiful way of verifying. So I can prime factorize this and I look at all the primes, all the powers. If I have 6 primes, then I can do it. If I don't have 6 primes, I cannot do it. In 120, there are only 5 primes. 120 is divisible by only 3 primes, 2, 3 and 5. But I'm saying 5 primes because there's a 2 cube sitting there. 2 is there 3 times and then a 3 and then a 5. So 2, 2, 2, 3, 5. I'm breaking it like that. And I still have only 5. I need to have 6. Therefore 120 doesn't work. Now let's look at 121, 0, 0. 1, 2, 1, 0, 0. 121 is 11 square. I know that. Into 100, which is 10 square. So it is 11 square into 2 square into 5 square. 10 is 2 into 5. Lovely. 2 plus 2 plus 2, 6. This seems to work. Brilliant. But how do I put the individual primes? I cannot say that the first guy have 11 and 11. The second guy have 2 and 2. Third guy have 5 and 5. I cannot have 11 square, 2 square, 5 square. Why not? Because I have different primes sitting here. So I'll put 11 into 2 here. 2 into 5 here. 5 into 11 here. 2 different primes, 2 different primes, 2 different primes. Brilliant. So if it adds up to 6, I can squeeze it in some form. I can figure out a mechanism to do this. So 1, 2, 1, 0, 0 works. What is the condition we have? Prime factorize it. In the prime factorization, if I think of square of a prime as 2 primes, cube of a prime as 3 primes, adds up to 6. I totally have 6 primes to deal with. Good to go. Right? Will all combinations of having 6 primes work? Or is there one other condition that we are missing? Think about that. So, but 1, 2, 1, 0, 0 works. Now let's check these two out. Mathematicians, if I know B works, I want to tell myself C and D don't work. I don't want to leave that there. So let's try it. What am I going to do? I'm going to do 240. I'm going to take 240 and prime factorize it. 240 is 24 into 10. 10 is 2 into 5. 240 is 4 into 6. 24 is 4 into 6. 2 square into 2 into 3. Or this is 2 power 4 into 3 into 5. Ooh, the powers add up to 6, so this should also work. It looks like 240 also works. Powers add up to 6. That's what we thought the main criteria. Now think about how this can work. I put 2 in 1, 3 in 1, 5 in 1. Make this 3 into 2. Make this 5 into 2. I still have one more prime left, but unfortunately for me, that prime is a 2. If I put here, we'll have 2 primes all right, but not 2 different primes. So if I have a prime power 4, I'm in trouble. Somewhere there'll be a square of that prime. I can put 1, 1, but I'll still be left with 2 remaining. That can't work. So that's the other condition. So the power should add up to 6. That's number 1. Number 2, nowhere should we have a 4. We cannot have 2 power 4, then it won't work. And I cannot create a pot that has 2 different primes. It has 2 primes, but they're both 2. That doesn't work. Which is why 240 does not work. 3000. 3000 is 3 into 1000. 1000 is 10 cube. 3 into 2 cube to 5 cube. I'm deliberately not writing this as 2 into 1500, 2 into 2 into 750, 2 into 2 into 2 into 375 and going step by step. That's the traditional way. Find each prime, isolate it, go step by step, divide all the 2's first, then the 3's, then 5's. The problem with that, I can think of a 10 as 2 into 5, 1000 as 2 cube into 5 cube. I'm done in one step. But if I do that long division method, I'll locate all the 2's, then I'll be dividing by a set of 5's, whereas thinking like this is very easy. And so your mathematicians are trying to do non-routine questions. Your methods also need to be intuitive, non-routine. Don't do it by the same old long division method, especially one where you take all the 2's, then all the 3's, then all the 5's. Doesn't work. 2 into 5 is 10. Extracting a 10 is so easy. 3 zeros here, 1000. 1000 is 2 cube into 5 cube. What is remaining? 3. You're done. Now this has 7 primes in it. Impossible. So I put it in 3 pots. Suppose I put 2 into 5 here. Again 2 into 5 here. Again 2 into 5 here. I still have a 3 remaining. That has to go somewhere. And wherever it goes, that number will be a product of 3 different primes. It won't work. My condition is not satisfied. Or this also doesn't work. 120 doesn't work. 12100 or 12100, 12100. That is the only possibility that can potentially satisfy this condition, which is why that statement itself is which of these could be the right answer, which has a potential of being right. And they're not saying find the right answer. They're saying of these 4, only 1 is even possible. The other 3 are not possible. So this question is beautiful because you have to find the one that is possible. The approach for that is go step by step, but don't just go mechanically step by step. The moment you try out 120, your mind should say, okay, 120 didn't work. What kind of number will work? Why didn't 120 work? Because I have 3 2's, a 3 and a 5. 2, 2, 2, 3, 5. If I think of 2 cube as 3 primes, 2, 2, 2, and a 3 and a 5, I still have only 5 primes. I need to have 6. We need P1, P2, P3, P4, P5, P6. P1 and P3 can be same. P4 and P6 can be same. But I can have, even if I count like that, I need 6 primes. So with just 5 primes, 3 2's, a 3 and a 5, I cannot manage it. Okay, super. Now I'll prime factorize and I'm looking for 6 primes. This satisfies the condition. I tried whether it works. It does indeed work. We're good to go. 240 has 6 primes, 4 2's, a 3 and a 5. But I cannot accommodate 4 2's because I can put 1 2 in one box, 1 2 in one box. The third box will end up having 2 2's. I need to have 2 different primes. That's where that collapses. So you add that condition. Keep that in mind. So you can go with trial and error step by step, but your mind should continuously be seeking method. Beauty in solving these questions is you go from trial and error to method, method to trial and error, and keep improving how you can find solution. That's very crucial. I'm going to go to the next question, but I'm going to do one change. A second. I'm going to go. Yeah, read this question. I'll come back here. The first question took a lot of time. The second one is also slightly tricky, but this set has a bunch of easy questions. Fine. When you're taking this exam, keep in mind that you need to solve only a certain number of questions. So pick and choose the easy ones, the ones you have a flair for, the ones in your comfort zones, in your favorite topics. But when you're solving, find the answer to everything. And so don't pick and choose questions now. Pick and choose questions in the exam. Now I want you to solve everything. And so where's the time pressure? Right? The GCD of A and 72 is 24. And the LCM of B and 24 is 72. Already complicated. There's already an A and a B. But not like we're talking about only GCD or only LCM. We're talking about both. So it's algebra also. GCD is just HCF, highest common factor. A and 72, 24. LCM of B and 24 is 72. Find the GCD of A and B and LCM of A and B, given that A is the smallest 3-digit number having this property and B is the biggest integer having this property. Complicated. Find GCD of A and B and LCM of A and B, given some conditions. And so this condition is most interesting. A is the smallest 3-digit number having this property and B is the biggest integer having this property. I'm going to find A first. A is the smallest 3-digit number having this property. What is that property? GCD of A and 72 is 24. The greatest common divisor of A and 72 is 24. HCF of A and 72 is 24. Right? Start with two numbers, their HCF is 24. First thing we can say, for both numbers, 24 is a factor. Lovely, 24 is a factor. So, 24 is a factor for 72. 24 is a factor for A. Lovely. Both conditions need to be satisfied. And then 24 should happen to be the largest possible common factor. Brilliant. It should not just be a factor, it should be the largest possible common factor. Now, 24 is a factor of A. The other way of stating this, A is a multiple of 24. Beautiful. So I'm going to narrow that down. I'm going to keep this aside for the time being. First statement tells us A multiple of 24. Or what could it be? It could be 24 itself. It could be 48, 24 into 2. It could be 24 into 3, 24 into 4, 24 into 5, 24 into 6, 24 into 7, any one of these. Right? So any one of those is possible. Lovely. Any one of those, A will be a multiple of 24 and 24 will be a factor of A. But A cannot be any one of those for the HCF to be 24, because 24 will then be a common factor of A and 72. It need not be the largest common factor. We still have to worry about that. Brilliant. Now what is the other condition that is given? We want to find the smallest 3-digit number having this property. Smallest 3-digit number. It's a 3-digit number. Let's eliminate non-3-digit numbers. 24 into 1, just 24, that doesn't work. Just 48 doesn't work. 72 does not work. 96 does not work. This is more than 100. 24 into 5 is 120. From here on, anything is possible. 120, more than 120. I don't know these numbers. One of these could be A. The smallest possible 3-digit number that A could be is 120. But think about this. Let's assume it is 120. What is the GCD of 120 and 72? I know you have a wonderful method of keeping these two together and doing this long division and doing step-by-step extracting factors, all of that. Don't do all of that. You keep on doing that, then we are not getting to the crux of the issue. We already know both of these numbers are multiples of 24. Also, we started with that. We said 72 is a multiple of 24, that we know. A is a multiple of 24, that also we know. So, write both of them as multiples of 24 and then think about the GCD. Don't do the same long division method. Then we are not using the idea that 24 is a factor of both of these numbers. So, I'm going to write this number as 24 into 5, 24 into 3. Both of them have 24 as a factor for sure, that I know already. So I'm going to write both of them as 24 into something, 24 into something. Brilliant. After we take out the 24, we have 5 remaining here, 3 remaining here. Subtract 24 out of these numbers, we have 5 and 3 remaining here. So what will be the greatest common divisor between these two? It will be 24. It cannot be more than 24. After I take out 24, I have 5 here, 3 here. They don't have anything in common. Those two numbers are co-prime, or 24 into 5, 24 into 3. For these two numbers, the highest common factor is 24. Okay. So A, the smallest 3-digit number that is possible for A, 120, or A equals 120. As it turns out, smallest possible value for A is 120, using the idea that A is a multiple of 24. That works for us. We are good to go. If it is the smallest possible number, automatically works for us. So 120 is A. So if A is a multiple of 24 and B is 24 into 3, can the HCF be anything apart from 24? If we take the next number, will the HCF again be 24? HCF of 24 into 6 and 24 into 3. What is the GCD of these two numbers? 24 will divide this, 24 will divide this. Brilliant. After that, we are left with 6 and 3. There is something in common there. 6 and 3, the common divisor is 3. Or 24 into 3 will divide both of these. Or these two numbers be written as 24 into 3 into 2 and 24 into 3. For these two, the common factor is not, the highest common factor is not 24, but 24 into 3, 72. Very, very crucial point sitting here. Comparing two multiples of 24. 24 into 3 and 24 into 5. Now we are comparing those two. 24 is definitely a common factor. That's obvious. I'm taking two common multiples of 24. Both numbers are multiples of 24. So definitely 24 will be a common factor. When will it be a highest? When will it be the highest common factor? When after taking out this 24, the remaining part is nothing in common, then it will be the GCD. There's something in common there, that will also go sit inside the GCD. So in all of these questions, you need to be very savvy. You've done this as a multiple of 24, you've taken this as a multiple of 24. So start from that. Write it as 24 into 5, 24 into 3. The moment you write it as 24 into 5, 24 into 3, you can notice that the GCD will be 24 and not something else. Right? Whenever you're writing two numbers of 24, two numbers that are multiples of 24, 24 is a common factor. Is 24 the greatest common factor, highest common factor? For that, you'll have to think about, after we account for 24, is there something else also still in common? That is, then that will come into the HCF. If not, then 24 is the HCF. And so, apply your mind by extracting the 24 and thinking about it. Don't go back to the long division method. Every time you go back to the long division method to HCF or LCM, then the mechanics and the method and approach are nice and long, but you're losing big nuggets. You know that both of these are multiples of 24. 24 is already a common factor. All we need to do is beyond 24, is there something else sitting there? So if you do the long division method, the whole idea, you're wasting whatever you have done to come to this point. So 120 and 72, 24 is a common factor. Take that, put in the bag, then think about the remaining. Got it? So A is 120, the smallest 3-digit number that satisfies this property is 120. Now let's go to the second part. B is the biggest integer having this property. What is B? B is such that LCM of B and 24 is 72. Or 72 is a multiple of 24, 72 is a multiple of B. 72 is a multiple of B, or B is a factor of 72. Clear? We want B to be as large as possible. Take B, go to 72. The LCM of 72 and 24 is definitely 72. That we know. 72 is a multiple of 24. 72 is a multiple of itself. 72 works. So we don't have to even worry about other factors of 72 because we want to find the biggest integer having this property. We cannot have B to be more than 72 because the LCM of B and 24 is 72. B is a factor of 72. The largest possible factor of 72 72. 72 works, we don't have to worry about anything else. B is 72. So we know A is 120, B 72. We want to find the GCD and LCM of A and B. Again, don't go back into your long division method. You can prime factorize this and get to the answer. You don't even have to prime factorize it. We already know one beautiful thing. All of our numbers that we are thinking about are linked to 24. Or 120, 24 into 5. 72, 24 into 3. I can think of 24 as 2 cube into 3. Prime factorize 24 also. Don't even need to do that. 24 I know, I'm writing it as 24 into 5. 24 I know, I'm writing it as 24 into 3. What is the HCF of these two numbers? 24. What is the LCM of these two numbers? It will be a multiple of 24, it will be a multiple of 5, it will be a multiple of 3. 24 into 5 into 3. I'm extracting these two numbers as 24 into 5, 24 into 3. Why 24 into 5, 24 into 3? Because I already know 24 is the HCF. 24 into 5 and 24 into 3, if you take out 24, there's nothing in common. 24 is the HCF, easy. When you're finding LCM, number should be a multiple of this and this. It should definitely be a multiple of 24. That nugget I have. It should be a multiple of 5, it should be a multiple of 3. These two cannot have anything in common. Why not? Because I know 24 is the HCF. So after I take out 24, the remaining should not have anything in common by definition. So 24 into 5 into 3, that is the LCM. This is 360, 24. So the GCD is 24, and the LCM is 360. Lovely. I'm going to go to the next question. Beautiful. Read this question, we'll discuss that. The sum and LCM of two positive integers x and y are given to be 40 and 48. Find the two integers. Brilliant. X and y, sum of these two, x plus y is 40. LCM of x and y is given to be 48. In several of these questions will usually start with prime factorization. And 48, prime factorize that. 48 can be written as 12 into 4. 12 is 4 into 3. 4 into 3 into 2 square. Or 2 square into 3 into 2 square. 2 power 4 into 3. In all mathematical, tough, non-routine, unconventional, different questions, usually when you're given HCF, LCM, don't fall back on your long division method. Think in terms of prime factorization. Now I'm going to forget about this question and we'll come to this. I want to thinking about the prime factorization of two numbers and then finding the LCM of those. I'm going to forget about 2 and 3. I'm going to think about different primes. Let's say I have one number is 5 square into 7. Another number is 5 into 7 cube. What will be the LCM of these two numbers? I want my number to be a multiple of this. So it should have 5 square and 7. I want my number to be a multiple of this. It should have 5 and 7 cube. Or LCM should be 5 square into 7 cube. It should be 5 square, this should be 7 cube. If we did not have 7 cube, it won't be a multiple of this. If we did not have 5 square, it won't be a multiple of this. HCF. HCF be 5 into 7. 5 into 7 divides this, 5 into 7 divides this. If I had even 5 square, it won't divide this. If I had 7 square, it won't divide this. That's the idea. So LCM and HCF, think in terms of prime factorization. Lovely. Now, I want to have two prime factorizations where the LCM is 2 power 4 into 3. Number 1 and number 2. Now, I could have one of the numbers should have a 3. Lovely. I'll put one of the numbers has a 3. It could have other things also. It could have a 3. The other number can also have a 3, but we cannot have a 3 square. Brilliant. This could have a 3, this need not have a 3. One of the numbers should have 2. let's say this number is 2. 2 into 3. Other number has 2 but not 3. 2 cube. Will the LCM be 2 power 4 into 3? Think about it. For these two numbers, the LCM is not 2 power 4 into 3. 2 cube into 3. The highest power of 2 that sits in any of these numbers only 2 cube. So why should my LCM have 2 power 4 in it? Not required. And so brilliant. Now this gives me a beautiful clue. If I want my LCM to be 2 power 4 into 3, one of the numbers, at least one of the numbers has to have a 3. Simple. Otherwise I can't have a 3 here. At least one of the numbers has to have a 2 power 4. If I have 2 and 2 square, the LCM will have only 2 square. If I have 2 square and 2 cube, LCM will have only 2 cube. LCM has 2 power 4 in it. That means at least one of the numbers should have 2 power 4 in it. So one of the numbers has 2 power 4 in it. One of the numbers has a 3 in it. Could be the same number that has both. The other number could have 2 squares sitting in it. Definitely one of the numbers has a 2 power 4 in it. What is 2 power 4? 2 power 4 is 2 into 2 into 2 into 2, 16. Or one of the numbers is a multiple of 16. True and true. Also, one of the numbers is a multiple of 16. Or if I have the two numbers as x and y, one of the numbers could be 16, it could be 32, it could be 48. And then the other number we need to think about. We know that sum of the two numbers is 40. If this is 16, this number should be 40 minus 16. It's 24. If this is 32, it should be 40 minus 32, which is 8. This cannot be 48. That cannot be a negative number. Or we have x and y are 16 and 24, 32 and 8. Now this 32 and 8, wonderful combination. 32 is a multiple of 8. 8 is a factor of 32. LCM of 32 and 8 is 32. Not what we are looking at. 16 and 24, LCM is 48. 16 and 24 add up to 40, get through. Key thing here, the LCM is 48. 48 is 2 power 4 into 3. At least one of the numbers should be a multiple of 3. At least one of the numbers should be a multiple of 2 power 4. 3 is a good starting point, but 2 power 4 is a brilliant starting point. I have one of the two numbers to be a multiple of 16. Either be 16 or 32. It cannot even be 48. I have 16 and remaining, 32 and remaining. 32 and remaining doesn't work. 16 and remaining work. And just to recap, the numbers were 16 and 24. 16 is 2 power 4. We know 24 is 2 cube into 3. LCM of these two numbers is 2 power 4 into 3 is 48. That condition is satisfied. We add these two, it is 40. That condition is also satisfied. That's the number we are looking for. X and Y are 16 and 24. It could be 16 and 24, 24 and 16. That doesn't matter. Beautiful question. Try this one. Using all the digits 1 to 9 only once, how many 9-digit prime numbers can you write? All the digits from 1 to 9 only once. And how many prime numbers can you write? Try this one. I'm going to try to fix this one. Take your time. Wonderful. So I want to find how many 9-digit prime numbers can you write. Usually in all of these how many questions, I like to find one. All I want to do is find one prime number. If I find one, then I'll be able to find the second, third, fourth. I don't even know how to find a prime number. I'm going to write the one nice number that I can write. Just 1, 2, 3, 4, 5, 6, 7, 8, 9. If this number were prime, good. If this number prime, then I already have one prime number. If this number is not prime, then I will try to write my first prime number. Brilliant. How do I check whether such a big number is prime? It's tough. You have to keep dividing by primes. The easiest prime I can think of is 2. Is this a multiple of 2 or is not? Is it a multiple of 3? Maybe it will be. How do I check that? Very easy. Add all the digits and then figure out 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9. Method for doing this. 1 plus 9 is 10. 2 plus 8, 10. 3 plus 7, 10. 4 plus 6 is 10. 10, 10, 10, 10. 4 tens 40. Plus 1, 5, 45. Sum of the digits is 45. Sum of the digits is 45. 45 is a multiple of 3. The number will also be a multiple of 3. That's it. Done. Why done? 1, 2, 3, 4, 5, 6, 7, 8, 9. Therefore, it's not prime. Now, what do I do? In this order, it is not prime. Maybe I'll write it in some other order. Maybe I'll say 5, 6, 7, 9, 3, 4, 8, 1, 2. 3, 4, 5, 6, 7, 8. Yeah, all 9. Will this be prime? This is obviously not prime. It's a multiple of 2. So maybe I'll try 5, 6, 7, 9, 3, 4, 2, 8, 1. Is this prime? It's not a multiple of 2. The next thing I'll check 3. Add all the digits. What will it be? 45. Or how many prime numbers are there? 0. Sum of the digits is 45. If you add all the digits, if it comes to 45, that number has to be a multiple of 3. If this is a multiple of 3, it cannot be prime. The only multiple of 3 that is a prime, 3. So this number is a multiple of 3, so it cannot be prime. Whatever way you arrange it, it cannot be prime. Or the number of 9-digit primes you can do. None. No 9-digit prime number that has all the digits appearing exactly once. Because any 9-digit number that has all the digits appearing exactly once has to be a multiple of 3, therefore it cannot be prime. A cube of edge 4 centimeters is painted red externally. It is then cut into 1 centimeter cubes. How many of these do not have red paint on any face? Oh, beautiful. Imagine a Rubik's cube, a 4 by 4 Rubik's cube, 4 by 4 by 4 Rubik's cube. I'm sure several of you have seen that. Rubik's cube will generally have 6 colors. This Rubik's cube had only 1 color. And so we can all imagine twisting, turning, all of that. This has only 1 color on all the sides. Brilliant. Then I break it into 1 centimeter cubes. First of all, how many of such cubes will be there? Think about it. So I have a Rubik's cube. Fine. So this is broken into 4 by 4. So pardon my drawing skills, but you get the idea. So 4 by 4, 4 by 4, 4 by 4. First of all, let's forget about how many will not have red paint on any face. Think about how many such cubes are going to be there. You have an 8 by 8 chessboard. How many squares will be there? 8 into 8, 64. You have 4 by 4 by 4 Rubik's cube. How many cubes will be there? There will be 64 Rubik's. How many will be there? 64 of those cubes will be there when you cut them. How many do not have red paint on any face? You think about how many have a red paint on any face. True. And we can subtract that from 64. We have the answer. So it's very tough to think about all 6 surfaces. For this Rubik's cube, there are 6 surfaces. The room you're in has 6 surfaces. Top and bottom, front and back, right and left. I'm going to think about only one surface. Let's say this surface. This surface has 16 cubes. All 16 of these fellows have one face painted red. This is painted red. Brilliant. So 16 cubes have one face painted red. We know there are totally 64. Of this 16 have to be eliminated. Not just this 16, 16 on each side. On each surface there are 16, 4 into 4, 4 into 4. All of those have to be eliminated. So I'll eliminate 16 cubes in each surface, 6 surfaces. 16 into 6 is 96. Hey, wait a second. I started with only 64 cubes. I'm now getting that 96 cubes have some side painted red. How is that possible? Something funny happening here. What is that funny thing? This corner cube, I'm counting here, here and here. This cube on the side, I'm counting here and here. So several of my cubes I'm double counting. I shouldn't do that. So I cannot just say this 16, that 16. Between this 16 and that 16 there is an overlap. Between this and this 16 there is an overlap. So I cannot just add up how many are there in each surface. and then find out. I need to have another mechanism. I'm going to say all of these outer cubes have something painted red. Some have these two painted red, some have all three painted red, this will have only one painted red. Everything on the external surface has something painted red. So I'm going to imagine this cube and then say I'm going to chop off every layer on the external surface. I have a 4x4 thing. I chop off the top. That entire set I'll chop off. Then I chop off the bottom. Then I chop off the right. I chop off the left. Then I chop off the front. I chop off the back. All of these have some face painted red. So it's like I remove all these front and back, right and left, top and bottom. Remove them. They have remaining. That remaining part will not have any face painted red. What is remaining is a 2x2x2 cube right inside this. Imagine front and back removed, right and left removed, top and bottom removed. So from 4, you're removing one layer on top, one layer on bottom, one on right, one on left, one on front, one on back. 2x2x2 sitting inside is a beautiful cube. 2x2x2 or 8 cubes have nothing painted. I have 4x4x4. I remove all the external surfaces. There will be a 2x2x2 sitting inside. It's beautiful. A regular Rubik's cube where you have 6 surfaces, 3x3, that will have only one cube that is totally not painted, one right sitting in between. So out of the total, 8 cubes don't have any surface painted. Again, this is slipped away. I'm going to start this all over again. Try this one. You have 5 pieces of 6 centimeter rods and 4 pieces of 7 centimeter rods. Using some or all of them, which one of the following lengths can you not measure? What can you not measure? Straight away, I'm thinking of this question as which one can you measure? 5 6 centimeters rod and 4 7 centimeter rod. What can you measure? Let's look at this. Can we measure 30? Can we measure 30? 5 6 centimeters rod. 5 into 6 is 30. Yeah, we can. Done. I'm going to think about what can I measure. I can measure 6, 12, 18, 24, 30. I can measure 7, 14, 21, 28. And I can measure any addition of these two. I can measure 18 plus 14, 12 plus 21, 24 plus 7, 6 plus 28. Any of those I can measure. If any of these numbers I can combine like that, then I'm through. And how can I combine? So let's say we want 29. How do we get 29? I have 6 plus 7, 14, 21, 28. I cannot get a 29. 6 plus 28 is 34. Doesn't work. 12 plus 14 is 26. 12 plus 21 is 33. 12 plus 21 is 33. So this I can measure. 2 into 6 plus 3 into 7. I'm through. Right? So 30 we can measure. 33 we can do. 18 plus 7 is 25. 18 plus 14 is 32. That's not possible. 24 plus 7 is 31. Yeah, 31 is also possible. And so 31 would be 24 plus 7. 30 is possible, 31 is possible, 33 is possible. Looks like 29 is the only one that is not possible. How do we get to 21? How do we find this number? Just trial and error, see what is possible. The other way of thinking about it, if all of these were 6 centimeters long, I have 9 of these possible. 5 plus 4, 9. So I can do 6, 12, 18, 24, 30 plus 6 I can have. Or from this, I can take one of these and replace with a 7. So I have 6, 6, 6, 6, 6 with me. Any multiple of 6 is possible. 7, 7, 7, 7 with me. If I take one of these 6's and replace with a 7, I'll get one more. So one more than a multiple of 6 is always possible. I can generate 13. Of 12, I can do 13. How? 1 6 I'll replace with a 7. 2 6's, 1 6 I'll replace with a 7, here I'll get 19. 2 6's I can replace with a 7. So any multiple of 6 plus 2 I can do. 3 I can replace. Any multiple of 6 plus 3 I can do. So those combinations I can do. 29, the multiple of 6 plus 5. 24 plus 5. I cannot replace 5 of my 6s with 7s because I have only 4 7s with me, which is why that is not possible. You cannot create a 29. Everything else can be created with some combination. Interesting question. Some donkeys and some chickens are there in the garden. I counted 64 legs in all, 20 heads in all. How many donkeys are there? 64 legs, 20 heads. Chickens and donkeys. What's the question trying to convey here? Every donkey has one head. Every chicken has one head. That is obvious. And so, leaving out fantasy movies, this is a possibility. And what is different here? Every donkey has 4 legs. Every chicken has 2 legs. So, the number of heads is nothing but the number of donkeys plus the number of chickens. But the number of legs, number of donkeys into 4, number of chickens into 2. Brilliant. In all of these questions, I really like thinking about extreme scenarios. What do I mean by extreme scenarios? Forget donkeys and chickens. Right? Assume it's only chickens. So, 20 of these, that will have 20 heads and 40 legs. All 20 were chickens. All 20 were donkeys. There will be 20 heads, 80 legs. No chickens at all, no donkeys at all. Very simple, either extreme. Our answer for number of legs is 64 only because we are in between. There are some number of donkeys and some number of chickens. Now think about this. From this, if I take one chicken and say, look, instead of having all 20 chickens, one of these I'll change and make it into a donkey. What happens? Chicken had only 2 legs. A donkey will have 4. So if I bring in one donkey, number of legs will increase by 2. 2 are going out, 4 are coming in. Right? So from 40, I'll go to 42. If I have 2 donkeys, I'll go to 44. 3 donkeys, I'll go to 46. So my number of donkeys is 1, and my total number of legs will be 42. Plus 2 will become 44. Plus 3 will become 46, and so on. Very simple. Every donkey gives me 2 additional legs. Additional from what? Additional from 40. I need to have 64 legs, or I need 24 more legs. Each donkey gives me 2, or I have 12 donkeys. Or my scenario, I have 8 chickens and 12 donkeys. Why 8 chicken? Totally there are 20 animals. 12 are donkeys, remaining 8 will be chicken. And this is obviously a very algebraic way of doing this. And I'm going to tell you that, but I want you to think in terms of if I take away a chicken, bring in a donkey, what happens? Okay? What is the algebraic way of doing this? Let's say the number of chickens, x, the number of donkeys, x chickens, 20 minus x donkeys. Why? Totally there are 20. X are chicken, the remaining are donkeys. Remaining from what? Remaining from 20. So there are 5 chickens, there are 15 donkeys. There are 10 chickens, there are 10 donkeys. 7 chickens, 13 donkeys. How am I finding it? I am subtracting from 20. This is x, this is 20 minus x. Each chicken has 2 legs. Each donkey, 4 legs. 2 times x plus 4 times 20 minus x will give us 64. Total number of legs, total number of legs. Add these two, you'll get total number of legs, which is 64. Solve for this, you'll get the number of chickens that are there. You want to find how many donkeys are there, or you want to find 20 minus x. You solve for this, you'll get x is 8, or 20 minus x is 1. Brilliant, that's the algebraic way of doing it. Not a big fan. You will do plenty of questions like this as you go subsequent classes. This will become autopilot easy. But I wanted to think about, if I take away a chicken, put in a donkey, what happens to my system? That is more important, that is more fun. Lovely, let's do this one. A and B are square numbers. The LCM of A and 140 is 560. LCM of B and 140 is 700. And the LCM of A and B, oh lovely, lovely. LCM of A and 140 is 560. Brilliant. What do I do whenever I'm given an LCM question? I think about prime factorization. So I'm going to prime factorize 140. Then I'm going to prime factorize 560. Then I'm going to go and attack 140 and 700. 140 prime factorization. 140 is 14 into 10. 2 into 7 into 2 into 10. 2 square into 7 into 10. 560. 560 is just 140 into 4. This number 2 square into 7, 2 into 5, sorry. 2 square into 7 into 5 into 2 square, or 2 power 4 into 7 into 5. Brilliant. Now let's look at A. We'll come to B later on. Once we crack A, B will fall in place. A, some number, 140, 2 square into 7 into 5, 560, 2 power 4 into 7 into 5. I'm going to think about the prime factorization of A. LCM of these two is this number. So a multiple of A should give us here. So A can have only 2 7s and 5s. A cannot have 11 or 13 or 3 straight away. Otherwise, the multiple of A will not be this number. This is the LCM. A can have maximum 1 7, maximum 1 5. It can have maximum 2 power 4. If it had 2 power 5, then LCM of these two will not be 2 power 4. It can have a 5, it can have a 7. Now, if A has a maximum of 2 power 4, but if A had only 2 power 1, then LCM of these two will only be 2 square. We're definitely having a 2 power 4 here, or A has to have 2 power 4 in it. Otherwise, the LCM won't be 2 power 4. In the LCM, there is a 2 power 4. The 140 has only 2 square. A has to have 2 power 4. Otherwise, the LCM won't be 2 power 4. After 2 power 4, it can have a 5 or not have a 5. It can have a 7 or not have a 7. That doesn't matter. The LCM will work. So A could be 2 power 4 or 2 power 4 into 5 or 2 power 4 into 7, 2 power 4 into 5 into 7. They're all possible. But there's one other beautiful condition that's given. It's told that A and B are square numbers. 2 power 4, 2 into 2 into 2 into 2, 16, which is 4 square. This is a square number. 2 power 4 into 5 will not be a square number. 2 power 4 into 7 will not be a square number. 2 power 4 into 5 into 7 will not be a square number. You're looking for a square number. We cannot have just a 5. If you have a 5 square, then that's easy. But only a 5, that won't work. Or A has to be 2 power. After this, we've got the method. Let's jump in. LCM of B and 140 is 700. I'm going to think about B. I'm going to think about 140. I'm going to think about 700. 140 we've already prime factorized. 2 square into 5 into 7. So 700 is 140 into 5, 700. Or it is 2 square into 5 into 7 into 5. Or it is 2 square into 5 square, 7. Lovely. So it is 2 square into 5 square into 7. So our number B should have a 5 square in it. It may or may not have a 7. It may or may not have 2 square, but it has to have 5 square. Why? If it had a 5 cube in it, the LCM will have 5 cube. If it had only 5 in it, LCM will have only 5. So our number should have a 5 square in it. Lovely. It can have a 7. It can have 2 or 2 square. Now, if it has a 7, it has to be only 7 power 1. If it had 7 power 1, then that 7 power 1 will make sure B is not a perfect square. We want B to be a perfect square, remember. So, B cannot have 7 because it can have only 1 7 maximum. If it has only 1 7, then B cannot be a square number. Can it have 2 square in it? It cannot have 2 power 1 in it, that we know. But it could have a 2 square in it. Right? Why so? Because if it has 2 square, B will still be a square. If it does not have 2 square, B will be a square, the LCM will remain the same. Or B has 2 possibilities. B could be just 5 square, or B would be 2 square into 5 square. Both are possible. Lovely. What did we know A to be? A 2 power 4. There are two possibilities for B. Maybe we'll get two answers. Think about this. A is 2 power 4. B could be 5 square. Which case LCM of A and B 2 power 4 into 5 square. Or A is 2 power 4. B could be 2 square into 5 square. In which case LCM would be 2 power 4 into 5 square. There are two possibilities for B, 5 square and 2 square into 5 square. But in both cases, the LCM turns out to be 2 power 4 into 5 square. 2 square into 5 square is 100. 2 power 4 into 5 square is 4 into 100, 400. Thinking of this as 2 square into 2 square into 5 square. This is 10 square, 100, 4 into 100, 400. B, there are two possibilities for B. B could be either 25 or it could be 100. Just 5 square or 2 square into 5 square. Two possibilities. But LCM of A and B is only one possibility. Beautiful question. Playing on the idea of LCM, playing on the idea of prime factorization, and then thinking about what is the LCM of A and B. Even though there are two possibilities for B, there's only one answer for LCM of A and B, that is 400. You think about this in this entire question, the moment I went to prime factorization, the moment we prime factorize 120, we thought about prime factorization of 700 as 140 into 5, prime factorization of 560 as 140 into 4. We thought about A as 2 power 4. We're thinking about B as 5 square or 5 square into 2 square. I'm not thinking of A as 16, B as 25. Once you've gone to the prime factorization world, live in that world. Don't come back and think about the numbers again. You've broken this into beautiful prime factors. You can think of A as 2 power 4. You can think of B as 5 square. You can think of 700 as 2 square into 5 square into 7. Don't think of it as 700. Think of it as 2 square into 5 square into 7. Only then you can extract HCF, LCM, all of that wonderfully. I think we're pretty much done with that. I wanted to leave you with one question. In our beautiful 4 by 4 by 4 cube question, we thought about how many did not have even one side painted. I wanted to think about how many have red paint on one face. How many have red paint on two faces? How many have on 3 faces? So think about all of that. I want you to figure out number of cubes that have 0 faces, number of cubes that have 1 face painted, number of cubes that have 3 faces painted, number of faces that have 2 faces painted. And then add all of this up and see if you get 64. I'm not going to do that for you to complete that, but that is an extension of that one beautiful question that we did. I want to stop with that. I'll catch up again with all of you guys Tuesday and again on Thursday. Tuesday and next Thursday. Hope you all had fun. Catch up with you.